Okay, in this video we're going to look at voltage and current and Kirchhoff's laws relating to voltage and current. So we have Kirchhoff's voltage law, KVL, and Kirchhoff's current law, KCL. Alright, so to get started, let's take a look at a battery. We need some concrete thing to discuss this. Alright, so here's a battery. And we've got that connected with wires to a light bulb. This is a symbol for a resistor. We're letting that represent the light bulb. Okay, so here's a really basic circuit. All right, now I asked you to watch the video about how batteries would work. Okay, so a battery is a DC voltage source, all right? And there's a chemical process that results in the separation of charge between the anode and the cathode. And when you connect the circuit, there's a flow of electrons moving back this way. So electrons go this way. All right. The voltage, we would mark that as plus and minus. All right, there's a polarity associated with voltages. So here is V. All right, so the idea here is that V is a measure of the energy required, or the work required, to separate charge. Okay, and let me move this. Okay, the units for that, one good thing about electrical circuits is the units are consistently SI. There's no English version of this, and so it's really easy. There's not a lot of unit conversions that need to happen. Okay, so the units are energy, which is in joules, required to separate charge. So joules per coulomb is the units that we use for voltage. Okay, so if you have a larger voltage, there's more energy available. And so you can think of this as potential energy. All right, because it is potential energy. In fact, a lot of times you'll hear voltage referred to as potential. All right. Contrast that to current. Okay, current is the flow of positive charge. Okay, and we all know electrons are what really flow, and electrons have a negative charge. So that you can think of current as flowing in the opposite direction of the electrons. Okay, so in general, when we have a little battery circuit, we'll reference the current to flow out of the top, out of the plus side, okay, because we know the electrons are actually moving the opposite direction. Okay, so current is a measure of charge flow, okay? So charge per unit time, coulombs per second. All right? And actually current is considered a base dimension, and so coulombs is the derived dimension. It's amp seconds. All right. You should also notice that because current is moving, it is a form of kinetic energy. All right, so I bring that up because there's potential energy and there's kinetic energy, just like with a mechanical system. Okay, so next, I wanted to cover Kirchhoff's current law. Okay, we call that KCL. Okay, the current law I think is pretty easy, and in my experience, students don't have trouble with Kirchhoff's current law. All right, so what we have here are some circuit elements that are connected. All right, so this would be called a branch of the circuit, or this part where you have an element that connects between 2 points. That's the branch of a circuit. All right, the place where things are connected is called the node. All right, so with that in mind, we can label branch currents. So maybe I would call this I1, okay? And maybe I'd call this branch current I2. And it doesn't really matter which direction I choose. I can randomly choose those, although later on we'll start to use some conventions on how we would choose that, and by using a consistent set of sign conventions, it's easier to get more accurate work. Okay, so maybe I would call this I3 as the branch current moving down through B. All right, so let's consider this node where these places connect together. All right, what would be the current at that node? All right, I'm sorry, what is the relationship of currents at that node? All right, so I think it's fairly obvious. KCL, the basic definition is that current in to the node is equal to current out. There's some versions of KCL where you reference all the branch currents or all the currents coming out of the node, and then if you do that, then the sum of currents going out of the node is equal to 0. But they all have to be referenced the same way for it to be that version of Kirchhoff's current law. All right, so I like to think of it as current in is equal to current out. All right, and that lets you write an equation. All right, so KCL for node 1 implies that I have I1 coming into the node. Do you see that? Here's I1, it's moving this way. So through the element, the current just keeps moving through the element. Here's I1 coming into the node. All right, I2 is also coming into the node because you keep moving it this way. So the currents coming into the node are I1 and I2, and the current coming out of the node is I3. KCL, piece of cake. Okay, what I think is a little harder is when we look at KVL. All right, so to take a look at KVL, I first want to draw the analogy between voltage and gravitational potential. Okay, so here's a picture of terrain, and we can draw points on the terrain. Maybe we'd call that point A. All right, and here's point B. All right, and we could use a reference point. All right, so let's say this is sea level. It doesn't have to be sea level, but that's a common thing for gravitational potential is to use sea level, and this would be our reference. All right, so with respect to the reference, the height, the gravitational potential is the elevation, it's proportional to the elevation at point A. All right, and the same thing for point B, the gravitational potential is proportional to the elevation with respect to the reference at point B. Okay, so to me it looks like in this diagram that point A is higher than point B. So let's talk about what would happen if we move from point A to point B. All right, if we do that, we're giving up potential energy. All right, so from point A to point B, we lose potential energy because point A is higher than point B. All right, so then what would happen if we move back from point B to point A? Well, we would gain potential energy because we're rising in elevation. Point A is higher than point B. And furthermore, if we went and summed around that loop, the sum of the potential energy is 0, right? We give up potential energy to go down to point B, we gain it all back coming back to point A. Right, and it didn't really matter how many points I had along the way. I could have, for example, here's alpha, here's beta, down here is gamma. Right, if I went from alpha over to beta, there's a certain potential energy that, I assume alpha is higher than beta. We're losing some potential energy, losing some more going down to point gamma, but then we gain it all back when we come up back to the same reference point. All right, so when we go around this loop, this closed loop, as long as it's a closed loop, the sum of the potential energy is 0. Okay, well that's what Kirchhoff's voltage law says. Kirchhoff's voltage law tells us that the sum of voltages around a loop is equal to 0. Okay, there's other forms of that. I like to remember it as voltage rises equals voltage drops. Same thing with changes in elevation. You know, potential energy due to rises is equal to the potential energies due to drops. Okay? Okay, next what I want to do is apply these ideas that we just talked about in terms of writing KVL and KCL equations for a circuit that I'm showing here. Now this is an abstracted circuit, right? We don't know exactly what's in the boxes. We haven't even talked about circuit elements at this point. But you do know with a circuit there's wires that connect things together. And so we can use this to do KVL and KCL examples. All right, so that's what we're going to do. We're going to start with KCL. And let's label this as node 1. And then we have nodes 2, 3, and 4. All right, to get started, you would need to define the branch currents. All right, and for now, let's just say that's arbitrary. We can just define those the way we want. All right, so I'm going to make I1 here. I'm going to make I2 here, I3 down or up. It doesn't really matter. I'm just arbitrarily referencing the direction. Okay, so I've labeled the branch currents. All right, at this point I can write a KCL equation for node 1. Okay, so what I have for that is current in equal current out. So I take a look at the node. All right, so I'm looking at this particular node and I see current I2 is moving in. I3 is moving out, and I1, right, we follow I1 this way, is moving in. So I1 and I2 are moving in, and I3 is moving out. That's KCL at node 1. All right, real quickly, let's do node 2. Okay, so at node 2, I look at the currents. You know, I'm redrawing these. You can mentally just do this without redrawing it, but here's I2. All right, I got I6 coming this way, and I5 is right here. So hopefully you see what I'm doing. The branch currents stay the same throughout the whole branch. Okay, so I have I6 coming in and I2 and I5 coming out. Okay, so the video quiz is, what is the current at node 3, the KCL equation for node 3? All right, so you should be able to do that. To apply KVL to some of the loops in this circuit. All right, so to do that, we need to assign polarities to the voltages. All right, so I look at each circuit element. If each circuit element is using energy, there's going to be a voltage difference between the plus terminal and the minus terminal of each element. Okay, so I can label those. It's arbitrary how I label those. All right, so I could do plus here, minus there for VB. I could do minus plus VD. Doesn't matter which sign is where. Plus, minus VF, minus plus VC, plus minus VE, minus plus VA. So I'm assigning these voltage levels as so. Okay, later on we start to do a consistent way of assigning these, but all the physics would work out if I do sort of random assignments, as long as I'm consistent throughout a circuit. Okay, so at this point what I need to do is identify loops. All right, and there's lots of loops in this circuit, so let's talk about an easy one. All right, we could move from here around this way back to here. All right, so that's a loop. All right, there'd be a starting point, and then we move in this direction around this loop. Right, so as we do a sum of potentials around the loop, what we know from KVL is that the voltage rises are equal to the drops. Okay, so let's write it. Let's write the KVL equation for this loop that I just showed. All right, so if I'm moving this way, the direction of the arrows, then what is VC? What is the voltage VC? Is it a rise or a drop? Well, if it goes from a plus to a minus, it's a drop. Okay, so VC shows up on this side of the equation. VD, on the other hand, as I move this way, is minus to plus, so VD is a rise. Okay, and finally, there's never a drop across a wire, right? The voltage drop across a wire is 0. All right, so when I move from plus to minus, VF is a drop. All right, so this is KVL for this first loop. All right, so let's erase this loop and do a different one. Okay, let's make a crazy loop. All right, so we could go starting at here, we could go this way. And that's a valid loop within this circuit. All right, now I could move this way, start right here, move this way around the loop. When you go through the loop, you have to have a direction. That's the definition of a loop, I suppose. All right, so we're going to move this way, and we're going to write a KVL equation around this turquoise blue loop. All right, so starting here at this point, all right, we run across VE, and that's a drop. From here, we run across VC. VC goes plus minus, so that's a drop. All right, at V, from moving from here to here, VD, I lost one of the signs. This was supposed to be a minus sign on VD, minus plus. Okay, that's a rise, so that shows up on the rise side of the equation. Okay, then we move on down to VG. VG is a drop. All right, so there's another valid KVL equation. Okay, so for the quiz, let's take a look at writing KVL equations around a different loop. Let's go starting here, let's move this way. Around this loop. Okay, so for the quiz question, write the KVL equations for this particular loop. All right, so that's a summary of KVL and KCL. That's one of the most important concepts that you have for circuits, and hopefully you can get some practice writing KVL and KCL equations.